Welcome all of you in the video solution for the GATE question paper. So here I'll be solving some questions from GATE Excel or Life Sciences questions, and the topic which I am covering in today's video is biochemistry, structure and function of biomolecules. So here is the question. So this is a previous year GATE question. So the question is being asked here is the dipeptide with least rotational barrier in the peptide bond is. There are 4 different options given. So before coming to the conclusion or for the correct answer, so let's know about the peptide bond. Okay. So a peptide bond is formed between two amino acids. So two amino acids bond together to form a peptide bond by dehydration. Okay, so if we'll talk about the structure of the peptide bond, so okay, okay, yeah. So simple amino acid structure. So there was an alpha carbon or the 4 valencies. Okay, so this is first carbon, another first amino acid. The next amino acid is where the alpha carbon. Okay, so these are two amino acids which were involved in the peptide bond formation. Okay, so this is a dehydration reaction. So during this reaction, one amino acid gives the carboxyl group, this carboxyl group. So in amino acid structure, we have one carboxyl group, amino group, hydrogen and R group. This R group varies and that brings the diversity in the amino acid structures. So one amino acid gives the carboxyl group and loses the hydroxy group from it. Another amino acid provides the NH2 group or amino group and loses the hydrogen. Okay, and these two together forms a water molecule and water is being removed. So this is a dehydration reaction that involves in the synthesis of the peptide bond. So this is also called as dehydration synthesis reaction. Okay, so after removal of water, this carbonyl carbon gets attached to the amino group to complete the structure. So this carbonyl carbon now added to this nitrogen. So this CN bond formation takes place, which is a covalent bond. So as in this structure, if we see it is nothing but an amino group, So this uh, uh, carbon takes the position of the hydrogen which is removed from the amino group. That is why it is also called as covalent amide bond. Okay, or most commonly peptide bond. Okay, so this is the peptide bond. So as this carbon and nitrogen, they are forming a single bond, but it looks a single bond, but it is not actually a single bond formation between these two, because of the presence of the lone pair on this nitrogen. Okay, so this nitrogen harboring a lone pair, which will allow the shifting of the electrons, and thus this peptide bond resonating structure in which this becomes partially positive, oxygen becomes partially negative, and this becomes a partial double bond character, which is not either single bond or double bond. It becomes a partial double bond character, a partial double bond structure. Okay, and due to the presence of the partial double bond, this is not, this becomes a very more or less rigid structure, not very movable bond. So the movement around this peptide bond is restricted. As long as it would be a single bond, the movement will be very easier around the bond. But because this peptide bond is no longer a single bond, it becomes a partial double bond. So that's why the movement of the atoms around this partial double bond becomes restricted. Okay, and this whole peptide bond, all the 6 atoms that are included with it, they all 6, 1, 2, 3, 4, 5, 6, all 6 forms a plane. Okay, and they forms a plane, and this is a planar structure is formed. Okay, so the movement uh, between these are restricted, between this peptide bond is restricted, but the movement so this is peptide bond, which is also called as omega bond. Okay, so this omega bond is a restricted movement, but this bond, the C alpha and the N carbon and the C alpha and the C carbon, okay, so here these are the pure single bonds. So the movement around these two bonds are not restricted. Okay, okay, and this also as it is joined with another moiety, this also forms another plane. Okay, this will also form another plane. So these two planes can rotate, but all the 6 atoms try to remain in one single plane, and the planar movement we can observe. Okay, the planar rigid structure would be there due to the presence of the peptide bond, but these two different planes where the C alpha and N and C alpha and C are bonding with each other, there the movement is possible, and that forms the proper tertiary or secondary structure of the protein, that provides the specificity to the protein structure. Okay, so the bond angle or the the dihedral bonds that are being formed between these two are called, so the C alpha and the C angle is called psi dihedral angle, and here the angle is phi. This is the phi dihedral angle, this is psi dihedral angle. So these two angle rotations are possible. So the value would be between 0 to 180 degree minus 180 degree. Okay, if we are considering one whole round movement, but all the movements are not possible, that are very restricted due to the presence of the bulky R group. Okay, that we'll discuss later. So as we can see here, okay, so as we can see here, so as this plane I drew here, okay, so here this is the CONH peptide bond, and I have drawn opposite to it the C alpha carbons. So this configuration which I drew here is a trans configuration. Okay, and if both the alpha carbons will be in the same direction, so if I'll draw here, okay, okay, like this, both the C alpha in the same position, so the R groups associated, that will also come in the same direction. This is the cis configuration of the amino acid. Okay, so just imagine being these two C alpha or the R groups in the same position. If they both possess a very heavy bulky R group, then there will be steric hindrance and there won't be structural stability in the amino acid or the polypeptide structure. Okay, because of the lots of steric hindrance. So to avoid steric hindrance, generally in nature the trans forms of the amino acids are favored. Okay, so the trans forms are favored except in case of proline. Okay, so if we'll see the structure here, as I was discussing, this is the trans configuration, this is the cis configuration. Okay, so cis configuration, both the C alpha carbons are in the same side, here the C alpha carbons are the opposite side. So in nature, for all the amino acid, the trans configuration is favored. The ratio, if we'll say, it is 1000 to 1 ratio of trans to cis. The occurrence of trans is 1000 to 1 cis configuration. Okay, but in case of proline, where this C alpha and the amino group are making a cyclic structure as a R side chain, so only in this configuration, in this particular configuration, if I'll say, so here both cis configuration as well as the trans configuration of the proline amino acid residues have the equivalent rotational energy. Okay, so if I will talk about the rotation around the peptide bond, in case of proline, if the proline is present as a dipeptide in any amide bond formation, the cis and trans both having the equivalent energy, so that's why equivalent rotation is possible. Okay, so in case of proline, there are 50-50 chances. So if there are 4 proline residues, there are chances 2 will be in cis configuration, another 2 could be in trans configuration. There is some ratios will be maintained. So if any polypeptide structure we are seeing, most of the amino acid will find in trans configuration, but if prolines are present, we can often see proline in cis configuration, because cis configuration of proline is also equally favored as the trans configuration. Okay, so here the basic or the uh, whole nutshell of this whole peptide bond is that the protein structure should be stable only when there is a less steric hindrance, and only when there is a less steric hindrance the rotation is possible around the bond. Okay, the question is ask a dipeptide with least rotational barrier in the peptide bond. Okay, so if can you answer? Can you try to answer which one could be the correct option from out of 4? What do you think? So here I'd also like to add about proline. So as we can see here itself, okay. So here proline is involved, right? So generally we have like this also I can write. This is the peptide bond structure, okay. But in case of proline, what we have is it forms a cyclic ring, okay. It forms a cyclic ring like this, right? So if the hydrogen or the peptide bond is formed between this carboxy group and the amino terminal of the proline, it looks like this, okay. So then the rigidity of the structure as compared to the normal peptide bond is lost because the N is now involved in a cyclic ring formation. Okay, so that is why when cis is present, the configuration or the movement around the peptide bond is visible as compared to here where planar structure is being formed, where the restriction, when the all 4 atoms remains in a single plane and inhibit the rotation, the planar structure, because of the planar structure. So this is not allowing the movement. However, when proline is present, this cannot inhibit the rotation and allow the rotation around the peptide bond. So this particular rotation is favored. So out of these 4 options, if we'll see, this one also have a planar structure of the peptide bond. Here also that plane will form. Here also peptide bond will present. But here if I'll see, but here if I'll see, here that particular peptide bond is formed, but that planar structure of 4 atoms cannot be formed. However, and here the in all these 4 cases movement will be restricted, okay, around the peptide bond. However, when this proline is present, then the movement will be allowed, the rotation will be allowed, okay, in case of this particular bond. So out of the 4 options, this particular option would be correct, where the planar form of the peptide bond is not visible. So this one is the, and this is my NPTEL reference. Thank you.